Hi, I'm Jaejun a PhD student of School of Computing at KAIST. I'm a member of the Big Data Intelligence Lab led by Professor Joyce Jiyoung Whang. I'll present our paper, InGram Inductive Knowledge Graph Embedding via Relation Graphs. Knowledge graphs represent known facts as a set of triplets where each triplet consists of a head entity, a relation, and a tail entity. For example, Hawaii terrain feature Hawaiian Islands. Knowledge graph completion is a task of predicting missing triplets. Classical knowledge graph embedding models assume that all entities and relations are observed during training, called transductive knowledge graph completion. For example, given this training graph, the task can be, what is the terrain feature of Honolulu? And the answer is Oahu. Here, Honolulu, terrain feature, and Oahu are all observed in the training graph. Like this, transductive knowledge graph completion aims to identify a plausible combination of the observed entities and relations. Recently, inductive knowledge graph completion has been proposed to predict missing links between new entities that are not observed at training time. For example, given this training graph, the task is to solve which country is Ottawa in, where Ottawa and the answer Canada are not observed in the training graph. To solve this problem, an inference graph is given. The existing inductive knowledge graph completion methods assume that the inference graph consists of new entities and known relations. An inductive knowledge graph completion model uses the training graph for training and uses the inference graph for the inference. For example, we predict the country of Ottawa in this inference graph. Even though entities are all new in the inference graph, existing methods still assume that the relations should be known at training time. That is, new relations are not allowed in the inference graph. Therefore, it is a transductive inference for relations. However, in many real-world settings, new entities can accompany new relations. In this work, we study how to handle these new relations appearing at inference time. We first consider the semi-inductive inference for relations, where the inference graph contains both known relations and new relations. For example, our task is to predict Ottawa, country, Canada, where the relation, country, is a known relation, or to predict Ottawa, official language, English, where the relation, official language, is a new relation. On the other hand, the inductive inference for relations indicates that all relations are new in the inference graph. For example, now we predict these triplets where the relations are new. To solve these challenging inductive learning problems, where both entities and relations can be new at inference time, we propose our model, InGram. Let me explain an overview of InGram. Given a knowledge graph, we define the relation graph where a node corresponds to a relation and an edge weight indicates the affinity between relations. Once the relation graph is defined, we can designate neighboring relations for each relation. Based on this relation graph, we compute the relation embedding vectors by aggregating the neighbors' embeddings. Similarly, we compute the entity embedding vectors by entity-level aggregation in the original training graph. The aggregation process is optimized to maximize the plausibility scores of triplets in the training graph. What InGram learns during this training process is how to aggregate neighboring embeddings and the interactions between the entity and relation embeddings. At inference time, InGram constructs the relation graph of the given inference graph and generates embeddings of new relations and entities by aggregating neighbors' embeddings using the learned weights during training, and perform link prediction in the link inference graph using the learned weights. Let me explain more, starting with constructing the relation graph. In order to handle new relations at inference time, we need some structured relationships between relations that can be used to calculate the relation embedding vectors. To define the relationships, we follow the intuition that if two relations share many entities, they should have a high affinity weight. For example, in this knowledge graph, acted-in and directed share multiple tail entities, and born-in and lived-in share multiple head and tail entities. Thus, we consider these relations close. We measure the affinity weights between two relations by considering how many entities are shared between them and how frequently they share the same entity. We compute the affinity between two relations by considering both head and tail entities with appropriate normalizations. Using this concept of affinity, we define the relation graph. As a result, we have this relation graph for this given knowledge graph. In the relation graph, we roughly divide the affinity weights by binning. For example, with 2 bins, we divide these 8 relation pairs into 2 groups. This binning information will be utilized in computing the relation embedding vectors. Based on the neighbors defined in the relation graph, we compute the relation embedding vectors by aggregating neighboring relations embedding vectors using an attention mechanism. In this process, we consider the relative importance of each neighboring relation to incorporate the local structure of the target relation. We also incorporate the global level of affinity by considering the bin's affinity weights defined in the relation graph. We introduce a learnable parameter C for each bin to differentiate the relations with different affinity levels. Intuitively, it would be beneficial to weigh larger for the embedding vectors of similar relations to the target relation. Therefore, we expect a high C-value for a bin with a lower index. We empirically observe that the C-values are learned as expected, as shown in this plot. Therefore, InGram successfully incorporates both the local structure and the global level of affinity when computing the relation embedding. Next, we compute entity embedding vectors. We update an entity embedding by considering its own vector, its neighbors' embeddings, and its adjacent relations. To compute the attention weight for the target entity itself, we consider all relations adjacent to the entity and compute the mean vector C bar. Then we concatenate the entity embedding vector and the mean vector, which are used to compute the entity embedding vector with an attention mechanism. Also, we concatenate the neighbors' embedding vectors and their adjacent relations, which are also used to compute the entity embedding vector. Finally, we aggregate all the relation-augmented embedding vectors using dynamic attention. We model the interactions between the entity and relation embedding vectors using a variant of this mode. Our model allows the dimensions of the entity and relation embeddings to be different. We define our loss by the margin-based ranking loss. When we train our model, we randomly re-split the fact set and the training set for every epoch. The fact set is used for aggregating neighboring embeddings, and the training set is used for calculating the loss. Also, we randomly re-initialize all feature vectors of entities and relations for every epoch. By employing the reinitialization strategy, InGram learns how to compute embedding vectors using random feature vectors, which might relate to the expressive power of GMNs. This dynamic split and reinitialization allow InGram to robustly learn the model parameters, which makes the model more easily generalizable to an inference graph. Since all existing benchmark datasets do not contain new relations in the inference graph, we create and use 13 real-world datasets based on NEL, Wikidata, and Freebase for experiments. We consider varied inductive scenarios with different ratios of new relations in the inference graph. As we explained earlier, we consider the inductive, semi-inductive, and transductive inferences for relations. In all these settings, all entities are new. We compare InGram with 14 different state-of-the-art methods, including subgraph sampling methods, BERT-based methods, and rule-based methods. This is the link prediction results when all relations are new in the inference graph. Due to scalability issues, Grail, Compile, SNRI, Indigo, and RMPI only run on the smallest dataset, NEL. Each bar indicates the MRR value. We see that InGram outperforms all baseline methods. This is the link prediction results when 75% of relations are new and the rest is known. We can also check that InGram significantly outperforms all 14 baselines. Last, we consider the case where all relations are known. NEL0 is our dataset, whereas NEL995 is a benchmark dataset. In these datasets, all entities are new. This is the setting that existing inductive knowledge graph completion methods consider. We see that InGram shows better performance than the baseline methods. In this work, we explore various inductive settings and define the relation graph to handle new relations appearing at inference time. We propose InGram, which learns to generate embeddings for new relations and entities solely based on the structure of a given knowledge graph. InGram does not require any extra information about the entities and relations, or the aid of rich language models. Experimental results show that InGram substantially outperforms 14 different state-of-the-art methods. Our codes and datasets are available at this link. Also, you can find more materials on our homepage. Thank you.